Now we shall study the Colpitt's oscillator. Colpitt's oscillator. The circuit diagram for this Colpitt's oscillator is a device which converts the DC into the AC with the desired frequency. Okay. So here we have one transistor, NPN transistor. The emitter biasing is in the form of RE and CE. Then this biasing is there. The voltage divider argument of the resistances R1 and R2. So this is resistance R1, this is resistance R2, and the second terminal of this one is to be grounded. Here the collector circuit in which the one of the choke is to be connected, the radio frequency choke RFC. And here we have given the VCC supply. Now the tank circuit consists of two capacitors, C1 and C2. This is C1, this is C2, and across a common inductor, placed across a common inductor here. So this is L, and the output is to be taken from this one as V out. So here is one of the coupling capacitors to be used, which provides the low reactance to the oscillations which are to be set up in the tank circuit. Okay. So this is a transistor Q, and the tank circuit which consists of inductor L and C1 and C2, the RF choke, radio frequency choke, voltage divider arrangement with the resistances R1 and R2, coupling capacitor C which usually the feedback which is to be brought from the capacitor C2 is coupled to the base of the transistor. So this is tapped at the center. These two capacitors C1 and C2 are to be tapped at the center. So this is the circuit diagram for the Colpitt's oscillator. It consists of a tank circuit, feedback network, and a transistor amplifier. So transistor amplifier along with tank circuit and feedback network can act as an oscillator. So this is a Colpitt's oscillator. Okay. Now the circuit operation we will see. As the so the frequency of this one is to be determined with the help of the values of the C1, C2 and L. Okay, which is dependent on the values of the L and C1, C2. As the circuit is to be turned on, okay, by applying the VCC, so that the capacitors C1 and C2 will get charged. As the capacitors C1 and C2 are get charged, so the electrostatic energy which is to be developed across these capacitors C1 and C2, as the L is in parallel with this one, this electrostatic energy collapses and the magnetostatic energy is to be developed across the inductance L. the capacitor is totally discharged through the inductance cell. Then further these capacitors are again charged, getting the energy from the inductance cell. Okay, that is the magnetostatic energy then converted into the electrostatic energy. So this is repeated again and again, that the electrostatic energy has been converted to the magnetostatic energy, and magnetostatic energy has been converted to the electrostatic energy, so that the oscillations are set up in the tank circuit. These oscillations set up in the tank circuit, that is, they are fed through the capacitor C to the base of the transistor, and which appears in amplified form across the collector, and the transistor action itself gives 180-degree phase shift. So while applying the energy to the tank circuit, okay, to overcome the losses across the tank circuit, whatever the losses in this tank circuit, they are to be overcome. They, as to meet the losses, the energy which has been applied. So this collector energy which has been applied to the tank circuit further onwards. Now here the choke, RF choke circuit decouples the AC mains from the VCC supply, so as which will not affect the output of the device. So here, whatever the oscillations which are to be set up, if they are of desired frequency, then you may get the output from this one. So the oscillations which are to be set up in this one are, that is, the frequency of that one is the given by 1 upon 2 pi under root of, that is, L into C. C is C1 and C2, therefore it is total capacitance we will take, that is CT. This CT is to be given as, the total capacitance is to be given as, that is C1 C2 divided by C1 plus C2. Okay. Now the feedback of fraction which is given through this to the tank circuit is given by, that is MV is equal to, so the voltage which appears across this one is in the form of, that is V out. The voltage which appears across the capacitor C1 is V out, whereas the voltage which appears across this one is the feedback voltage VF. So if you draw the another diagram over here, so this is like this, that is this capacitor 1 C1 which is to be applied across the common inductor L, and this is the capacitor C2. So this is L. So now here we are getting the voltage which is to be taken out from the device, that is V out. Voltage which is to be developed across the capacitor C1 is to be taken out as the V out voltage, whereas the voltage which has to be developed across this one is nothing but it is a feedback voltage which we are feeding to the transistor, and is further amplified, and that amplified, it is to be amplified in such a fashion that to, as the energy which is to be given to this tank circuit to overcome the losses. Okay, so this is the voltage across VF is 180-degree out of phase as that of the voltage across this C1. Okay, so this MV is to be given in the form of VF, the feedback voltage, divided by the V out, and this is nothing but the reactance of the capacitor 2 divided by the reactance of the capacitor 1, and the reactance of the capacitor is inversely proportional to the capacity of the capacitor. Therefore, this is 1 upon C2 divided by 1 upon C1. This will give you, that is C1 divided by C2. That is, the feedback fraction in V is to be given as C1 divided by C2. Okay, so this is about the Colpitt's oscillator. As the circuit is turned on, the capacitor C1 and C2 are charged. As the capacitor C1 and C2 are to be charged, this energy which is to be developed across the capacitor C1 and C2 is now collapses, and the energy is to be developed across the inductor L. This repeats, the process repeats, so that the oscillations are to be set up across the tank circuit. So tank circuit of this oscillator consists of C1, C2 and L. Now, whatever the oscillations which are to be set up is to be fed to the transistor across the base of the transistor, which appears in the amplified form across the collector circuit. So this amplified the output of this transistor is to be given to the tank circuit, the energy which is to be supplied to the tank circuit to overcome or to meet the losses of the oscillations which are to be set up in the tank circuit. Okay. Now here the RF choke is to be used to just to decouple the AC mains from this supply, and which will not affect the V out of the device. Now the oscillations which are to be set up in this one are depend that the frequency of operation is given by, that is F is equal to 1 upon 2 pi under root of LCT, where CT is nothing but it is the total capacitance of the capacitors, that is to be given in the form of, that is CT is equal to C1 C2 divided by C1 plus C2. Now the feedback fraction which is to be given to this device, that is to be given by M is equal to Vf, the feedback voltage, divided by the output voltage. Now the voltage which is to be developed across this capacitor C1 is nothing but it is a V out output voltage, and the voltage which has to be developed across the capacitor C2 is its a feedback voltage. This voltage is 180 degree out of phase as that of the voltage across the C1. Now this whatever the feedback which we are giving to the tank circuit, okay, to overcome or to meet the losses, that should be in phase. See here 180 degree phase shift is to be given by this circuit, whereas the transistor action itself gives the 180 degree phase shift, so that whatever the energy which is to be supplied further is in phase with the oscillations which are to be set up in the tank circuit. Now these oscillations which are to be set up in the tank circuit, if they are of desired frequency, so we can get the output from this device. So the frequency of that one is to be given by F is equal to 2 pi under root of LCT, that is 2 pi under root of LCT. Now the feedback fraction is to be given Vf divided by V out, and Vf is, that is the reactance across the capacitor C2, and this is the reactance across the capacitor C1. As the reactance is inversely proportional to the capacity of the capacitor, so that the C2 is 1 upon C2 and the C1 is 1 upon C1. Therefore, this comes to be C1